Hufting's inequality relates the number of trials, where you're flipping basically a weighted coin, the failure probability, the likelihood that the observed rate of the heads coming up is different by more than epsilon from what the actual rate is. It relates those quantities to each other as follows. Now we can rewrite this in terms of, this is in terms of the success probability. We can rewrite this in terms of the failure probability. So the failure probability is going to be small as the number of samples goes up. As the number of samples goes up, this becomes a very large negative number. E to a very large negative number is very close to 0, 2 times that, and that's an upper bound on the actual failure probability. The real failure probability might actually be lower than this quantity. So let's define delta bar to be our failure probability bound. So if we solve this equation for n, what we find is that the sample size that we need, n, as a function of the desired failure probability bound and the error probability, bears this relation here. It's polynomial in 1 over epsilon and 1 over delta, and it tells us how many flips we're going to need to guarantee that we meet this failure probability bound in terms of having an estimate that is epsilon close to the real answer. So that's what the Hufting bound tells us. In class I had a little trouble because I carried this inequality through, but I think the right way to think about this is that we're relating a failure probability bound to the sample size that we need to be assured that we achieve that bound. And we're not actually relating the failure probability to that quantity. So here's a kind of an odd bandit setup. Imagine that we've got 3 bandits. Each of them has some probability of producing a 0 and some probability of producing a 1. And what we're going to do is we're going to walk up to this system and we're going to pull arm A and observe whether it comes up 0 or 1. If it comes up 0, we're then going to pull arm B, and whatever B spits out is going to be our payoff. But if A spits out a 1, we're going to pull arm C and see what value it produces to figure out what our payoff is. Now we don't know what the probabilities of 0 and 1 are for A, B, and C, but what we're going to be able to do is take some number k and pull each of these arms k times for A, k times for B, and k times for C, and use that to make estimates of what the outcomes of the A, B, and C arms are. And what we'd like to do is choose a k so that we can make the following guarantee. We want to estimate the payoff of this system as a whole to within epsilon with probability 1 minus delta. Now the question is, how many times should we pull each bandit? What value of k should we use to make this guarantee? And here's a hint. You should use the Hufting bound and apply the Hufting bound to each of the arms. But you have to keep in mind that the epsilon and delta that you use for each individual payoff estimate, so if when you apply the Hufting bound to A and to B and to C, the epsilons and deltas that you get are going to translate into some other epsilons and deltas for this system as a whole. So you're going to need to set epsilon and delta for each individual machine so that the epsilon and delta that you get for a whole are, well, epsilon and delta. Don't just literally use this epsilon and delta in the Hufting bound because you're going to get the wrong answer. You're going to have to think about it a little bit more than that. To make this concrete, we're going to say that epsilon is 0.1 and delta is 0.02. So given those values, how many times do we need to pull all the arms? We're going to pull them all the same so that we can make this guarantee at the end.